Today's lesson is on the magnetic field caused by a current carrying wire. So one of the basic premises of electricity and magnetism is that a current carrying wire will produce a magnetic field. Now, that magnetic field, like all fields, whether it's a gravitational field, an electric field, magnetic field, has both size and direction. So if we run current through this wire, or in a picture we run it through this wire, that current will cause or produce a magnetic field. Magnetic field has both size and direction. The size part is easy, right? We talked about this yesterday. Makes perfect sense. If I run more current through this wire, we're going to have a greater magnetic field associated with it. The closer I get to the wire, the greater the magnetic field. The farther I get from the wire, the smaller the magnetic field. So it makes perfect sense for our magnetic field B to equal I up on the top, direct relationship, R on the bottom, indirect relationship. Get our constant of proportionality, mu sub 0 over 2 pi. And there is our equation for the size of the magnetic field caused by a current carrying wire, right? Now, magnetic field B is measured in Tesla. That's our unit for magnetic field. And that describes the size of the magnetic field. Now, the direction of the magnetic field is much goofier. And we introduce what is the first of our right-hand rules of magnetism and electricity. All right? So that direction of the magnetic field we can get by the right-hand rule. All right? So it's really our first right-hand rule. How do we implement the right-hand rule? Well, we take the right thumb on our right hand and we put it in the direction that the current is flowing. Now, a couple things. Number one, first off, we're talking about a direct current, a current that goes from point A to point B, as opposed to an alternating current that alternates back and forth. That's number one. Number two, when we use our right hand, we are assuming the flow of positives, or what's called conventional current. We talked about that a little bit yesterday. In reality, we have flow of negatives, but we often envision it as the flow of positives. If we were talking about the flow of negatives, all the same rules apply. We would just use our left hand. But for the most part, we talk about the flow of positives, and we will use our right hand. And to implement the first right-hand rule, you take your right thumb and you put it in the direction of the current. And then your fingers will wrap around the wire in the direction of the magnetic field then. Now remember, what did we talk about yesterday? The direction of the magnetic field is always the direction that the north pole of the compass would point. So when I say it's the direction of the magnetic field, yes, but always remember, where does the direction of the magnetic field relate back to? What will happen to the north pole of a compass if we put that compass in the magnetic field at that particular spot, right? So this picture right here is what we get if we implement the first right-hand rule. If I take my right thumb and put it in the direction of the current, and then wrap my fingers around this wire, that's the direction that the magnetic field will take. Now you can see that the magnetic field takes the form of concentric circles around that wire. Now, we have two dimensions here on this board. If you're doing it in the paper, there's two dimensions. You're watching this on a video screen, that's two dimensions. All right? The best way to view this is with respect to this in three dimensions. All right, so if we take and imagine a positive current running this way in this wire, then I would take my finger, my right thumb rather, right, and I would point it in the direction of the current in that wire. What's the magnetic field look like? Well, it's concentric circles that wrap around the wire in the only direction really that your fingers can go. Your fingers can't go backwards. They can't do this because your hand doesn't go that way. So if my thumb goes this way, the concentric circles have to be directed this way. All right, now a couple of things here. All right, number one, you can imagine an infinite amount of concentric circles that get further and further and further and further away. In other words, there's a concentric circle with a radius of 1 centimeter. There's another concentric circle with a radius of 1.5, and another concentric circle with a radius of 2, and so on and so forth. Well, each of those concentric circles has a different R value. that's going to coincide with the different strength of the magnetic field. So as we get further and further and further and further from this wire, the R value goes down. But we still have a concentric circle that is at any particular radius. And this really goes on infinitely far away, although obviously the farther away you get, the less of an effect. Now, what again is the direction of the magnetic field? Well, we say it takes on the form of concentric circles around this wire, but in reality, at any particular spot, it is the direction that the north pole of the compass would point. Well, if we kind of like use our hand as a tangent, right, then we can show the direction of the North Pole if we do this three-dimensionally. So if my thumb is going in this direction, then over top of this wire, my fingers are pointing towards the backboard. Well, what would that indicate? Well, my fingers, right, the shape of the magnetic field is in concentric circles, but in reality, at any given point, my fingers are pointing in the direction of the magnetic field. And again, what's the direction of the magnetic field? The direction that the north pole of a compass would point. So over the top of this wire, my fingers are pointing towards the backboard. That means that the direction of the magnetic field is towards the backboard. That also means then, if I were to put a compass up here, the north pole of the compass would point towards the back of the room. If I loop my fingers around and now I'm at the back of the wire, then my fingers are pointing downwards, which means if I were to put a compass back here, the north pole of the compass would point downwards. Underneath the wire, there's a location down here. Is there a magnetic field down here associated with the current carrying wire? Absolutely. If the current is going in this direction, then down here, my fingers are pointing out towards the camera. Again, that means if I put this thing right here, the north pole of the compass would point out towards the camera. Now, if I reverse the direction of the current, then everything reverses. So now if the current is going this way, I take my right hand still, and now those circles are going in the opposite direction. Those circles are going up over the top, and then they curl around and they come underneath over this way. So what's that mean? That means if the current is flowing in this direction, then above the wire, the magnetic field is pointed out towards the camera. In front of the wire, the magnetic field is pointed downwards. And underneath the wire, the magnetic field is pointed in towards me. So the direction of the magnetic field is essentially the tangent to any of these circles, specifically with direction associated with which direction my thumb will point, because that will indicate which direction my fingers have to wrap around the wire. And that's the first right-hand rule for electricity and magnetism. Now, basically what that sets us up is that leads us into the next idea, right? And the next idea kind of describes, really, or we can use a compass to describe that. If I take a magnet and I move the compass, right? So I can come right here, right? If I take this magnet and I move the compass near, or I move the magnet near the compass moves. Now, a compass is nothing more than a kind of like a floating, pivoting magnet. So this compass has a magnetic field that surrounds it, and this magnet has a magnetic field that surrounds it. At any time two magnetic fields interact, we get a magnetic force. So this compass has the tendency to stay right where it is unless an unbalanced force acts on it, just like anything normally would, right? So how can I get a force to act on that compass? Well, I can get a force to act on that compass by bringing another magnetic field in close contact with the magnetic field associated by this compass needle. Here's a magnetic field. Here's a magnetic field. There's two magnetic fields. Anytime I have two magnetic fields, I get a magnetic force produced. That's a super important concept for us. Anytime I get a magnetic field, anytime two magnetic fields interact, a magnetic force is produced. So super big idea for us. It's essentially how motors operate. So if I have a magnetic field that is pointed this way, and I were to bring the compass in contact with that magnetic field, then the compass would pivot around, just like I just showed you on the video. Well, what does that have to do with a wire? Well, if I run current through this wire, I'm producing a magnetic field. There's one magnetic field. If I bring that current carrying wire near another magnetic field, perhaps one made by a bar magnet, more than likely one made by an electromagnet. But if I bring this current carrying wire into another magnetic field, then there's actually a force that gets produced. So for instance, here's this magnetic field. Now let's take a wire, right? And let's run a wire with current running downwards. So now the original magnetic field that I had up here on the board is magnetic field number 1. The current carrying wire here produces a magnetic field of its own. That's what we talked about over here. So now, all of a sudden, how many magnetic fields do we have? Well, we have 2 magnetic fields. Those 2 magnetic fields interact to produce a magnetic force. That is essentially how a motor operates. And tomorrow's lesson will be about the physics of this magnetic force. Forces are vector quantities. So tomorrow we've got to come up with an expression for the magnitude of this force and the direction of this force. And that's tomorrow's lesson. For today, I want you to view the videos that I'm also going to post out on Schoology, and then do the worksheet that I'm going to post out on Schoology as well. Have a good day.